Hello everyone, welcome to GradDr. So, in this lecture, we will talk about the escape velocity. So, what is this escape velocity? So, it is the minimum velocity with which a body must be projected up so as to enable it to just overcome the gravitational pull. So, if this is a planet and this is the gravitational field, so what will be the minimum velocity through which a body can be projected out so that it just overcome the gravitational pull of the planet? So for this, if we will write the work done to displace a body from the surface of the earth from its radius, suppose r is capital R, to infinity. Infinity means to just outside the gravitational pull of the earth or some other planet. So here we will talk about the earth. So the work done is from capital R to infinity, capital G m upon x square dx. So the formula will be, after integrating, we will get minus capital G small m 1 upon infinity minus 1 upon r. So it will be W equals to G m upon r. So this is the work required to project the body so as to escape the gravitational pull now. So the work done should be equal to the equal amount of the kinetic energy. So if we will provide the velocity VE, suppose this velocity is escape velocity, we call it escape velocity, then the kinetic energy should be half mVE square, and this kinetic energy should be equal to the work done, equals to capital G upon r. So from here we will get the equation as VE equals to under root 2 capital G capital M upon R. Now since we know that small g is gm by r square, so capital Gm will be equal to gr square. Now if we will put this, so we will get under root 2gr. So VE will be under root 2gr. Now if we write small g as 4 by 3 pi rho g capital R, then we will get the escape velocity as under root 2 into 4 by 3 pi rho capital G R into R. So this will be R under root 8 by 3 pi G rho. So this will be the escape velocity in terms of the density of the earth. Now let's talk about some important points, the key points. We can see that escape velocity is independent of mass, independent of the mass of the body. Of the body and direction of projection. Next will be, it depends on the reference body. So greater the value of m by r or g into r for a planet, then greater will be the escape velocity. That means more escape velocity is needed. Third, if we talk about the Earth, so for the Earth, we know that small g is 9.8 meter per second square and radius is 6400 kilometer. So escape velocity will be, if we will put that, we will get 2 into 9.8 into 6.4 into 10 to the power 6. So we will get 11.2 kilometer per second. So this is the escape velocity for a body to go out from the gravitational pull of the Earth. Fourth, a planet, suppose a planet will have atmosphere. If the velocity of the molecule in the atmosphere is, so we talk about the VRMS for the molecules, and VRMS we know that it is 3 RT by m. This will be lesser than the escape velocity. Fifth point, if a body is projected with a velocity less than the escape velocity, then what will happen? So the body will reach to a certain maximum height, some maximum height, and then two things will happen. It may orbit around the planet or may fall back. Sixth, if we want to calculate the maximum height attained, then we know that at maximum height the velocity becomes 0. So applying the law of conservation of energy, we will see that the total energy at surface will be equal to total energy at height h. So at the surface it will be minus gmm upon capital R plus half mv square. At height h, the kinetic energy will be 0 since velocity is 0. This will be minus gmm upon R plus h at certain height h. So if we will solve this, we will get that v square upon 2, this m will be cancelled out, will be equal to gm 1 upon r minus 1 upon r plus h. So after solving this, we will get g capital M h upon r plus h. Now, if we will write this as 2g capital M v square r, so this will be r plus h upon h, and this will be 1 plus r upon h. So if we will calculate the height, so height attained will be h is equal to r 2 capital Gm upon v square r minus 1. How we will get this? We will transfer 1 to here, and from some numerator and denominator transfer, we will get the small h. Now, since we know that the escape velocity v is 2 capital Gm upon r, so v square will be 2 Gm upon r. Substituting this into h, so we will get h equals to r ve square upon v minus 1, and we will get it as r v square upon ve square minus v square. So for maximum height h, the expression will be r v square ve square minus v square. So this is an important point, and try to remember this because these are asked in examination directly. Now what happens if body is projected with velocity greater than the escape velocity? Then applying the conservation of energy, by conservation of energy, writing same as total energy at surface equals to total energy at infinity, because this time the body will leave the gravitational region of the planet. So this will be half mv square minus g capital M small m upon r equals to half. It will attain certain velocity since it is greater than the escape velocity. So this, and since it is at infinity, that means it is out of the gravitational pull of the planet, then the work done or the potential energy will be 0. So this will be v dash square equals to v square, cancelling out the small m, v square minus 2 capital G m upon r. So from here, by solving this, from here we will get v dash square as v square minus ve square, since ve is under root 2 gm by r. So ve square will be 2 capital Gm upon r. We have substituted this here. So from this expression we will get the velocity will be under root difference of square of these two velocity. That is, the body will move in interplanetary or interstellar space with velocity this. Now let's talk about the escape energy. So what will be the escape energy? So escape energy will be total energy at the surface. So that will be sum of kinetic energy plus potential energy. So kinetic energy at the surface will be 0, potential energy will be minus Gmm upon r. So escape energy will be capital G m upon r. This will be the same work done but in positive value. Now let's talk that if the velocity of the body is equal to the velocity of light, then what will happen? If escape velocity is equal to velocity of light, then from such bodies nothing can escape, even the light, as in the case of black hole. So what we have written, that if the escape velocity of the body is equal to the velocity of light, then nothing will be escaped from that body. So as in the case of black holes, the escape velocity is equals to the velocity of light. That means the gravitational pull of black holes are so much that even light cannot escape from it. So from this we can write as, instead of V as the formula under root gm by r, 2 gm by r, so V square will be 2 gm by r. Let's suppose that V is the velocity of light, then the radius of the black hole can be calculated. So what will be the radius of the black hole? It will be 2 gm upon velocity of light. So by putting the mass of different planets or stars, since stars becomes the black hole and there are certain conditions when a star can become a black hole. Actually there are 3 stages of stars: the white dwarf, neutron star, and black hole. Since our sun is also a star, so the criteria for defining that what will happen if the star explodes or dies, then it changes into these 3 forms: the white dwarf, neutron star, or the black hole. So we write the mass of the sun as ms, that is solar mass, and everything is compared to the mass of the sun. And our sun, when it will die or if its fuel gets erased, then it will convert into a red giant. Although this is an advanced part and these are not going to come in your examination, but a person should know about this. So I hope you have learned the escape velocity. Thank you so much.